É extremamente importante para mim deixar claro que esse trabalho envolveu pelo menos da ordem de 30 pessoas que foram meus colaboradores, meus alunos e sempre se tornaram meus amigos. Se é que não começaram como amigos. É um ingrediente que eu posso dizer, na minha experiência, nada mistura melhor do que amizade e colaboração, especialmente científica, porque quando a gente faz ciência, a gente não produz algo imediato. Então dá tempo de curtir a amizade. De resto, eu vou deixar claro que eu vou demonstrar um software no qual eu tenho trabalhado há muito tempo e espero que funcione, porque existe uma coisa chamada efeito demonstração. De fato, ele ameaçou pifar. Okay. So I'm going to go to English, some kind of English now. The title of this talk is something that I was not sure I could really afford about 2 weeks ago. So I'll be talking about how to solve Riemann problems in something that approaches an automatic way. I should insist that all I'm talking about is the result of work of at least 30 people who were either my students, my collaborators, but all, either they started or they became my friends. And friendship is a major ingredient to make scientific work profitable and pleasurable. I cannot imagine it could be otherwise. Okay, let's see if I remember what I have to say. First of all, I'd like to explain that this talk is in honor of Eli Isaacson, who made fundamental contributions to the development of Riemann solvers and Riemann problem theory between the 80s and the 2000s. He passed away this year after a long period of oblivion from us, unfortunately. He's probably the nicest person I ever met. And of course, he was a brilliant problem solver. I don't know anyone, I don't know anyone that could solve a problem that you could state quickly and he would solve it even faster. He would put to shame any Olympics. So I should also say that the software that resulted from his effort and other people's efforts is called now Eli's instead of some ridiculous name like RPN2 or something. So from now on it's Eli. The Eli solver is an advanced Riemann software and is going to become available soon, or if you're adventurous, now. It was developed and used at, well, I put IMPA, but that's recent. It started at Courant, where I got my degree, with my sitting on an old Tektronix, which was a graphical computer, not computer, graphical monitor. That was a good call at the time. It was put in there by the administration to encourage mathematicians to use it, and I took the hint. I was hooked. I don't see how else can one display scientific information except through these kind of devices? Nowadays, it's any monitor. Well, this is a TV, by the way. Okay? But it's an excellent monitor. So it was developed there, it was developed at Madison, it was developed at Laramie, it was developed at IMPA, at Pura, years and years, with another friend who passed away a long time ago, Paulo Paes Leme. Okay. Something else. I dedicate this to my wife, to whom I owe all I've got. And she's the nicest person on earth, even though she tries to hide it. Well, since my son is here, I have to thank him for the many times that when he was a boy and came with his friends in the living room and told his friends, please be quiet. My father is looking at the ceiling. Therefore, if he's looking at the ceiling, he's working. Be quiet. So I had a lot of understanding from him along the years. I have been and continue being very lucky with my family. Okay, business. How did I come about Riemann problem? Riemann is a famous name. I worked in a number of areas about almost, 150 years ago, but that was not the reason it came through. We were interested in studying the flows of fluids in porous media. And the application was, of course, not mentioned here, but it was oil recovery, petroleum recovery. So there are some steps in a typical method for simulating how petroleum flows. Well, remember that it's petroleum, water, and usually gas. It's a mixture of fluids. And Grimm, in '66, concocted his famous random choice method. That was in '66. I arrived there in '70-something. And he said, well, the method I have is not very good for simulation. Could we do something about it? Okay, so we concocted the front tracking method. Oops. And that requires solving Riemann problem as, where is this? Here. It requires solving Riemann problem as a necessary stage. Okay. So we tried to solve the Riemann problem, and we came up with a solution of a particularly simple one, which this is in a flow in 2 spatial dimensions, looking from above. You're injecting water you're injecting water from here and taking a picture at different times of where is the displacing water. And there are 2 plots in here. One which is the exact position which can be found by hand, and the other is the numerical. And so the largest discrepancy is here. It is very, very small. So the front tracking method was extremely accurate. Of course, what it did was not a simulation. It was a calculation. We put in there all the theory known to us. If you put in something, if you put in a solution of a problem, all the theory that you know, well, either you know nothing or you get something not bad. Putting all the theory you know is very hard because it's not taking the equations as they come and discretizing, which is what people expect to do when they do simulation. They want a simple numerical method. This is not simple. In fact, to implement front tracking requires computer science, because you have to put in description of fronts, description of all the objects that appear in liquid flow or fluid flow. And that happened. The Glim's group immediately started churning computer science. Glim took a while to recognize it, but he did, but not faster than I did. I should say that I was lucky that to collaborate with him. This paper is an example of such collaboration with either the first or one of the first papers on front tracking. The reason being is that nobody in his group could program. And I have spent a few months taking an undergraduate Fortran course. I was in my doctoral, and I had to compete with students much younger than I, who got much better grades at all the homeworks they did. For them, programming was trivial. For me, it was not. And that was my only C in my doctoral program. I was shocked. But actually, I learned a lot. But, okay, no grades to offer. Okay. Not too long from after we started working, perhaps a year and a half later or 2 years later, there was a brainstorm led by Glim about what problems to solve using this new front tracking method. So he said, let's do, for instance, the three-phase flow in porous media. What's that? That means the flow of water, oil, or gas. But in a situation more complicated than the one that I showed you earlier. So I don't think that the equations were written this way. These are the equations that we solve here. This one for this model here. And that was done the year my son was born. So it's been a while. And I said, I want that one. That one meant three-phase flow in porous media. I'm still working on it, but now I'm presenting results. On the other hand, the next day, Glim came with half of the solution. He drew a triangle on the board, a triangle that that was here a while ago, a saturation triangle that describes a position here is to describe how much oil, water, and gas you have, and then started making pictures near the boundary. Everything he said about the behavior of the fluid that could be represented in the boundary was right up to now. But luckily for me, it was wrong in the center. based on what he knew, he said, oh, in 2 weeks you solve it. Well, I promised him not to mention this again. But now I cannot resist. He has actually supported this work throughout my career in scientific and French terms. So for this particular model, I guess I have a list of collaborators here. The steady one have been Bradley Plor, Eli Isaacson, and Pejota Paisleme. And then the younger ones. Another aspect of this model is modeling of oil recovery by injection of foam. We mean, you know, the foam you can shave with is the same foam. Okay? So it's like soap. So it washes the oil out in some way. So I mentioned some people whom I worked with on foam at Delft. Bill Rossen and Elham Ashori. I should say something about Elham. Elham was, or I should say, is from Iran. She and her wife came to the Netherlands, which is an extremely friendly country to foreigners. And they like it there. Elham, in her degree, did extremely well. And we started looking in something that for them was extremely abstract mathematics. For us, it's rather concrete, but she had to learn it on the spot. We produced a number of papers. She got the prize for the best thesis of the year and a few other prizes. I think she's not the sole female student I had, but extremely smart. What's sad about is that in order to support her husband to get his degree, she gave up her career. And that was because she was expected to do. I protest. I think she would have been able to do both. So if you have female students, make sure you pay attention to their special needs. Could happen in other places. Okay, so this is a little bit of showing what an image of when you try to use the computer to find the Riemann solution. When you inject, here is an injection of a mixture of water and gas in a petroleum reservoir. So we use what's called a wave curve method. Curve is because everything that you can get from this code is curves. Find the intersection of curves. Something is important there. So this is just to show you how a screen looks like. And a solution is like this. And of course, only an expert can say that you have, you have a shock here, another shock here, rarefaction wave. But I believe that's the end of my... Oh, the other thing, it's important to take into account... I'm sorry I went overboard. Well, I still have to show something here. We are taking into account, finally, we are taking into account the small diffusion terms that exist and are essential. Should say that Luis, who's here, made important, to me at least, important progress in this aspect, and perhaps they are definitive. Well, you never know in science what's definitive. Okay. How about this automatic? A wave group consists of a repetition of certain smaller groups. You see this stands for a shock, rarefaction, shock, rarefaction, shock, rarefaction. They repeat itself. We found a way to automatically describe such a sequence when you add a new pair. You see there's a repetition of pairs. So since we found a way of finding all such solutions, by repeating this procedure we find them all that satisfy certain restrictions. Not yet. Then we impose the restrictions, and that's what we call here trimming because of viscous profile. Well, now we have a method to find all possible solutions, if it's right. And this it would be an automatic Riemann solver that complete. That has been a problem in this area. You either find not enough solutions or you have too few solutions. Okay, so perhaps when there's such progress, people say, oh, now we don't need you anymore. It's the opposite. More scientific opportunities are created. Please, some of my most direct collaborator will show you a little bit of the aspect of this. São dois. I personally have been spending a non-trivial amount in time in computer science, and it's always an effort because it's not easy. Vai. Okay. Só mostrar.
This is a ERP1, the software to Riemann solutions. Now you construct the slow wave curve. It's a shock, rarefactions, and composite waves. And the next step is construct the fast wave curve, and the software make this after calculating the intersection between the two curves, and show the solution of the Riemann problem between the left state here and the right state here, and you can to see what is the solution. This point not to see, but when you move the red line here, you can to see how is the construction of the Riemann solution. That here you can to see the sorry.
You went to sleep or no?
Okay. The rarefaction of the two states, I think that is saturation of water and oil. And here you can to see.
Fácil.
Yeah, here is the shock next constant state, other rarefaction that here in the green line. Okay. Quickly. Stop scanning. Yeah. Then here you see the red line and jump here to here because here to have to shock. After to have to other rarefaction and finally to have to the last shock here. That's it. This is a classical solution that you can do construction, but other more complicated solution is when you use, for example, transitional shock that is.
So he's going to recompute for different values.
Okay.
Okay? Say when. Okay, he did. He just moved. I don't know if you saw it. It was rather quick. Okay, so that's one capability. Should we show a little bit? Ismael, please. So Luis showed you something, and now we go to the other, the Eli software.
So I've been working with Dan for maybe 2 years on this new software for human problems, and my part is basically to construct software to study viscous profiles. So under Dan's supervision, I've made many tools, and I'm going to show you some of them. So here we have a Hugoniot, and you can see it's colored according to the eigenvalues so that we can analyze the viscous profiles. So we want to know if there's a connection between two states. The left states right here, and every single one of those in the curve are possible right states. We want to know if there's a connection between the left and one of the right states. So for example, we can draw those invariant manifolds. Those are orbits living an epsilon away of the equilibriums in the direction of the eigenvectors. If they leave one equilibrium and end on the other, so we have a connection.
Why does this show up and disappear?
This monitor is a little bit.
Oh, it's a monitor.
So notice that we try to make it fast enough so that you can jog around and see how things go.
Oh.
And this is here we try to show as many orbits as we can. Actually, we can show even more. And then we can see, by defining one left state and one right state, how things flow in the phase space.
Mostra de novo aí.
Can you repeat, please, the flow?
Soto, isso é para você.
And we try to make it draggable too.
Você está vendo?
So that you can see how things change once you move on the Hugoniot logs.
Ok. Acho que tá bom. Já
And
você.
then we have some. Up to now, I've showed you some results with the viscosity matrix being the identity, but we can also show you results with the general viscosity matrix.
Posso? Ok, agradecer.
Okay.
Okay, agradecer. I want to thank our crew for demonstration, and you're welcome to go downstairs in the lab to see more. This is just a little bit. And I guess that's it. That's the end of what I want to say. Thank you.
You mentioned parallel for this computation? CPU.
Parallel. This is, can you hold this? Não, é mostrar isso aqui. É preciso, puxa fora, é possível. Só mostrar que existe. Quantos processadores tem isso?
Only 4.
This has 4 processors.
But it's not processing on CPU.
This is a supercomputer with 4 processors. Well, we have 16 processors,
But
and seems to be doing most of what's needed. Huh? No, it's not. It's not. It doesn't require not. Well, this is for a system of 2 equations. Okay. 3 equations will be many times more. So in fact, we can eat any computer time there is. That's in fact, most applications can, right? So, but I would say that computer power is not as important as the quality of the software that you put in, both organizational and mathematical.
So how long will it take to solve a million problems?
Which problem? Riemann problem?
Yeah,
If you don't know it,
like left and right, solve a million times, different right and
no.
how long will it take?
You have to develop all the theory. You use this to develop all the theory.
No, but
So-
I like to use this as a good enough example,
Pardon?
as a good enough scheme. So I solve a Riemann problem, find the flux for each connection between two.
How long do it take to find the theory of the problem? Solve all the,
Well, your code has,
huh?
your software, you develop.
My software takes a few weeks of people standing on it, using it, and in 2 weeks you have a paper. How long does Godunov give you one answer? Fraction of a second.
Yes.
How many time you have to run it until you have a paper?
Yeah, I'm more concerned about how long it takes. Suppose I want to use good enough.
It's different. It's different. Every single amount of theory that there is programmed in there. You have to program it. So it's in completely different spirit. It's not scientific computing. It's machine proof to some extent. So actually, well, okay, if it's in the category of problems that you already solved, then Ismail, how long does a simulation take compared to a good simulation take of a problem that you know?
Well, in my experience, much more time to run a simulation than to solve a Riemann problem. We can solve instantly. Depends on.
So if it's something that the theory of which you have already developed, it's instant. If it's not, you have to develop it. Is this good or bad? It depends whether science is your objective or not. If you only want the answer, perhaps it's not a good idea. If you're an engineer that wants to do a quick calculation in order to see that whether something is in danger, then you should not solve the Riemann problem. Okay? But that's what mathematicians do. You ask them a question, they come with science instead of the answer. What do you expect from me? That's actually an important point. What we do here with this code is not produce answers, it's produce science, in summary. And so you have to put up with it. You have to learn it. Some people don't like it. That has been quite a problem and a challenge and a virtue of this approach over all my career. Does that answer?
Yep.
Okay.
I have a variation on the last question. If you wanted to do a true Godunov scheme, you would need this whole answer, right, at every step. But is there an intermediate step you can do without fully resolving? Like,
Yes, but at a certain point you can develop approximate Riemann solvers. And that actually would be an excellent tool for this. I have not pursued this. I should say in favor of simulations that we have coupled the two codes to compare. And using both codes, one that does simulation and the other that does theory, in fact, increases productivity by, I don't know, at least tenfold. Tenfold, because otherwise, you sometimes the profile gives you a hint. On the other hand, the final answer, you need to adjust the profile to the theory. And that requires, if it doesn't adjust, then you're in bad luck. You have to work more. Okay, I guess that's what I had to say on this. But you were asked about speed, right, all the time when you develop a scheme.
Yeah, I say this because I wrote a paper with you, and we saw that the Godunov, you can get very good answers with a very coarse mesh.
Yes.
But it takes a lot of time to solve one problem between two cells.
Uh-huh.
So if you can solve this fast,
Yes.
it will be very difficult to beat those Godunov schemes.
By all means. But approximate Godunov scheme, that's what that is. That we could look into that. But either it falls in something, the theory of which we know a little, or otherwise we have to develop it. But I don't think you dislike developing theory.
I remember in our program that is a scalar with hysteresis, you have like 27 ifs.
Yeah.
A lot of time.
Okay. So I guess in summary, this is not a quick way to solve problem. It's the quickest. It's a quick way to establish the theory for a problem. Oh, Fred, don't you think that? Even though most of the time you just stare at the screen, doing nothing, right? You look at the image.
You have to extract the information that you have to extract the information provided by that.
Right, you have to see, since it's, yeah. Okay.
I want just to mention that Dan is one of the most impressive person I've seen. Like somebody that can deal with the administrative people, with the computer science people, get people together. Like as you see here, it's like he has a lot of childs. Okay? He's always concerned about the personal issues about each one. With the secretaries, it's really, you're very unique, Dan, just to tell you this.
Thank you.